You have already come across a choice model in your earlier statistics course. You dealt with logistic regression and learned how to interpret the results in terms of odds and odds ratios. If logistic regression does not ring any bell at the moment, it might be a good time to review your notes from previous class. This lecture builds directly on your knowledge. We will now deal with a logistic regression model and learn how to interpret the results in terms of the predicted probabilities. So far in this course, you've primarily dealt with continuous outcome variables. In classical linear regression model, we estimate the expected mean or conditional mean for each one unit change in our independent variable. However, when our dependent variable is discrete or dichotomous, estimating conditional mean is not terribly informative, as you can imagine. Thus, we can choose to estimate the likelihood of a certain outcome. For example, the likelihood of voting for a certain candidate. You have already learned what the equation looks like when it's expressed in terms of the log of odds as depicted in figure 8. However, for many people, odds are not particularly intuitive way to gauge real magnitudes of an effect. So now compare the model written in terms of the predicted probabilities. To do so, we use the inverse logit function to transform the effects of the independent continuous variable into a range between 0 and 1 of probabilities. In this particular equation, however, we did not preserve the linear functional form as in figure A. What does that mean for us in practice? To answer this question, we need to talk very shortly about the shape of the logit function. In figure C, you can see that the shape of the logit function is the steepest right in the middle and then tapers off at each end. It is precisely for this reason that you can probably now guess that the estimated slope does not have a constant effect. Instead, it changes depending upon which value we hold our independent variable or our independent variables at. So in figure D, we have taken a simple regression model and have transformed the model into predicted probabilities. It is because the coefficient does not have constant effect in terms of the probabilities that we cannot just interpret the coefficient directly as we did for our interpretation in the log of odds. Let's continue with an example. We hypothesize that older voters will be more likely to vote for a Republican candidate than younger voters. Below, you can see an output we estimated in R. Now, we could choose to interpret the effects of age in terms of odds you have already practiced before. Recall that to interpret the coefficient, we would exponentiate the intercept and the slopes. For even more intuitive picture, we can express the coefficient in terms of percent change by simply subtracting the exponentiated coefficient from 1 and multiplying by 100. So in our case, we can conclude that for each 1 year increase in the voter's age, the estimated odds of voting for a Republican candidate increases roughly by 0.2%. That is not a very large change indeed. We can also express this outcome in terms of predicted probabilities by using the inverse logit function in R. Here we have to select, however, a particular value for age, since we know that the slope is not constant across the entire range of the values of our independent variable age. Let's, for example, look at the predicted probabilities for voters of age 16. That is the minimum voting age in the US and also the minimum age of voters in our data set. We add the intercept and the coefficient, multiply by the value of age we just selected, and transform this equation using the inverse logit function. So now the predicted probabilities of voting for Republican candidate of 16-year-old voters is roughly 50%. We can do the same for other values, such as the oldest voters in our data set. You can compare simply by looking at the predicted probabilities that are of voting for Republican candidate for the oldest voters that are now roughly 54%. Now, we also can fit a multivariate model and include race as an additional predictor. In the output, only the coefficient for race turns out to be statistically significant at a 95% confidence level. However, or beyond 95% confidence level. However, for the calculation of the predicted probabilities, we must include all covariates we included in our original model that we estimated just a minute ago. Now, it is very important to emphasize that our choice of values that we decide on to hold our independent variable at is likely to have a very substantial effect on the resulting predicted probabilities. So it's important to actually do it with a reasonable caution. Consider, for example, here, we want to compare two types of voters, old and white voters, and old and non-white voters. Now, we included intercept and both of the coefficients now into the equation. And the predicted probabilities for old and white voters is roughly 57%. And the predicted probabilities of voting for a Republican candidate of old and non-white voters is roughly about 21%. You can see that this is quite a sizable difference. Now, in some cases, especially working with survey data, for example, our outcome variable takes on 3 values or more. And the outcome categories then can be, for example, ordered, or they can be also nominal. In those cases, ordinary logit model would not be able to handle these extra categories. So in those cases, we should use a multinomial logit. In our next model, we look at the effect of predictors such as age, gender, or race on income. Income, in our case here, is a categorical variable, ordinal, measured in income percentiles and contains 5 categories. We fit our model and obtain a large number of estimates. And I have to say that it can look a bit daunting compared to what we are used to from the models we worked with so far. But I think that once you identify what each part is, I hope it becomes a little bit less intimidating. Imagine that each line is a separate logistic model with separate estimates and intercepts for each of our variables. You have also probably noticed that we have only 4 categories displayed here. So what is going on here? Well, we have omitted 1 category from the output. The lowest income percentile, the 0 to 16 income percentile category. As a result, each of the coefficients is now estimated relative to the omitted category. So let's take, for example, the coefficient for female in the second income category. Directly, it means that for women, the multinomial log of odds of being in the second income category compared to the first income category decrease by 0.32. Now, that's not entirely interesting outcome and very, very strange in terms of the real magnitudes of these effects. If we exponentiated this coefficient and transform into percentage change, we obtain what is now called relative risk ratio. It's kind of like a brother from odds ratio, but a little bit more complicated because now it is a ratio of 2 ratios. One for the referent group, the first income category in our case, the 0 to 16 percentile category, and one for the comparison category, which in this case we selected the second income category, the 17 to 33rd percentile category. So for example, for the first coefficient, the relative risk ratio for females of being in the second category compared to the lowest income category is decreased by roughly 26%. Or the relative risk ratio for whites to be in the highest income category compared to the lowest income category is 7.8 times higher, or 678% higher. That is, of course, a sizable effect. Again, we can also calculate the predicted probabilities for each income category for specific constellation of values that are of interest to us. In this example, we would like to understand the probabilities for white women of average age to earn income in all of our 5 categories, all of our 5 income categories at the same time. So from the output here, you can see that, for example, white women of average age have predicted probability of about 15% to earn income in the lowest income bracket, the 0 to 16 percentile, and about 5% of earning in the highest income bracket, that is the 96 to the 100th percentile.